In this video, I will lecture about spectroscopic methods. Spectroscopic methods fall into the fourth unit of our chemistry course. The fourth unit is instrumental methods of chemical analysis. There are several techniques of analytical in nature to study chemical molecules, especially organic molecules. These are spectroscopic methods, chromatographic methods, and other potentiometry, calorimetry, etc. Important ones are spectroscopic and chromatographic methods. Spectroscopic methods. In this video lecture and the next one, we will see about spectroscopic methods precisely. What is spectroscopy? The name itself indicates spectroscopy, to see with the help of light. So, spectroscopic methods are the methods through which we can see molecules or the matter with the help of light. So, how to identify any organic molecule with the help of spectroscopic methods? We can use different types of spectroscopies. For example, we can use CHN analysis, through which we can determine the empirical formula of a compound. For example, if we take methanol CH3OH as the compound, empirical formula for this compound consists of CHO. So through CHN analysis technique, we can predict the empirical formula of a compound. Similarly, through mass spectrometry, we can analyze molecular mass of a certain compound. And in a similar way, UV visible spectroscopy will give us information about conjugation in any organic molecule. Presence of double bonds or triple bonds is called conjugation. That kind of conjugation can be obtained. Information about that kind of conjugation can be obtained from using UV visible spectroscopy. Similarly, IR spectroscopy or infrared spectroscopy can be utilized to obtain information from functional groups present in a molecule. So, IR spectroscopy or infrared spectroscopy can give us information about functional groups present in a molecule. In a similar way, H1NMR and C13NMR spectroscopies can give us information about number and arrangement of atoms. In this course, in this video lecture and the following one, we will exclusively study in much details about IR spectroscopy and UV visible spectroscopy, because we have IR and UV visible spectroscopies in our syllabus. But before going deep into these two types of spectroscopies, we must first understand the nature of light and what are the different components present in the light, and also what are the different terminology that we use while studying spectroscopic techniques. Light is an electromagnetic radiation consisting of both electric fields and magnetic fields. Electromagnetic spectrum consists of different components present in the light, ranging from gamma rays to radio waves. And all these components are arranged either in increasing order of wavelength or decreasing order of wavelength. For example, in this slide, if we observe gamma rays which have least wavelength, which is 10 raised to minus 12 meters, which is a picometer, is kept at the leftmost part in this chart, and the rightmost is radio waves, which consist of 10 raised to minus 2 meters wavelength. And we can see other components of the light like X-rays, UV visible radiations, and infrared radiation, and also microwaves. So this arrangement of decreasing wavelength from gamma rays to radio waves also indicates that the frequency and energy from gamma rays to radio waves increases. We know that as wavelength increases, frequency of the radiation and energy of the radiation will decrease. And as wavelength decreases, frequency and energy of the radiation will increase. And in between in between ultraviolet and infrared, we have visible region, which is essentially VIBGR that you have studied in your previous classes. So based on the different components present in the light, we have different regions which correspond to different energy transitions. For example, if you look at this slide, we have regions X-ray, UV visible, infrared, microwave, and radio frequency. And there are corresponding energy transitions which are bond breaking, electronic, vibrational, rotational, and nuclear and electronic spin. So essentially it means X-rays have higher energies, lower wavelengths, high frequencies, which can be used to even break the bonds between atoms in molecules. In a similar way, UV visible radiation correspond to electronic transitions occurring in molecules. Electronic transitions are the transitions of electrons from lower energy states to higher energy states. So UV visible radiation is not sufficient to break the bonds, but it is sufficient enough, it has sufficient energy enough to transfer electrons from lower energy states to higher energy states. And infrared radiation has even lesser energy compared to the other two, X-ray and UV visible. So infrared radiation can only vibrate the bonds between atoms in the molecules. So vibrational energy transitions only will occur by the utilization of infrared radiation as the source to excite the molecules. In a similar way, microwave radiation can cause rotational energy transitions. Rotations about the bond axis occur in molecules. So only rotational energy transitions can occur through usage of microwave radiation. Similarly, radio frequency, which is utilized in NMR, nuclear magnetic resonance spectroscopy, can give information about nuclear and electronic spin present in a molecule. So as I have told you, we will discuss deeply about infrared spectroscopy and UV visible spectroscopy only. So coming to infrared spectroscopy, as I have already told you, conventional infrared spectroscopy will give us information about functional groups present in a molecule. Advanced infrared spectroscopies like Fourier transform infrared spectroscopy (FTIR) will give us information about quantitative information of functional groups. For example, if you take methanol CH3OH, it has a functional group OH, alcohol. This can be identified with the help of infrared spectroscopy. And using FTIR, we can quantitatively determine the amount of OH containing groups or OH containing molecules present in a sample. And in addition to other techniques like magnetic resonance techniques, structural parameters in alkyl and aromatic groups can be obtained, and ratio of alkyl to aromatic groups in paraffins or petroleum can be determined with the help of infrared spectroscopy. And FTIR is particularly important for application to the higher molecular weight determination, higher molecular weight solid constituents of petroleum. So functional groups present in higher molecular weight solid components in petroleum can be determined using FTIR. Similarly, it is also possible to derive structural parameters from infrared spectroscopic techniques or data, and these are saturated hydrogen to saturated carbon ratio in a sample, paraffinic character, naphthenic character, methyl group content, and paraffin chain length. So these are all can be determined using IR spectroscopy, and we will see applications of IR spectroscopy later. So this slide represents a typical cartoonistic way of indicating the functional groups and their vibrational frequencies or vibrational wave numbers. So here we have wave numbers ranging from 1000 centimeter inverse to 4000 centimeter inverse almost. And if we observe from 1000 to 1500 centimeter inverse, we have fingerprint region. You know that even identical twins will not have identical fingerprints. They also will have different fingerprints. Their fingerprints vary from each other. In a similar way, functional groups in certain environments will have their own fingerprint wave numbers or fingerprint regions, which are represented in the form of wave numbers here. So if you look at the graph, there are single bonds, double bonds, triple bonds that can be identified using IR spectroscopy. For example, C double bond C, C double bond O, C double bond N. Those fall from 1800 to 1500 centimeter inverse region. Triple bonds fall from between 2300 to 2100 region. C triple bond C and C triple bond N, like that. OH and NH functional groups will give IR bands around 3000 to 4000 centimeter inverse. So this essentially indicates that we can determine different functional groups present in different molecules using IR spectra. But before going even deeper to IR spectra, we need to consider understanding some terminology in spectroscopy like wavelength, wave number, frequency, amplitude. And to understand these things, we will consider light as a wave. You know that light has both a wave-like character and particle-like character. So light as a wave representation can be like this, as represented in this slide, like wave. If you look at picture A, there is a broken black line which we can call as 0 point or baseline, and there are mountains and valleys, maximums and minimums, or maxima and minima. The maximum is called crest, C-R-E-S-T, crest, and minimum is called trough, TROUGH. So the distance between two crests or two troughs is called wavelength, and the distance from baseline or the broken black line to either maximum or minimum is called amplitude. And if you look at picture B, we have wavelength of violet light, which is represented here as 400 nanometers, and in picture C we have IR or infrared radiations wavelength, which is 800 nanometers. So if you compare both pictures B and C, we know that infrared radiation has almost twice the wavelength of violet radiation. So when the wavelength is twice, its energy will be half, based on the relation between wavelength and frequency. And when you consider light as a particle, we know that E equals to h nu, or E equals to hc over lambda. E is energy of a single photon, h is Planck's constant, nu is frequency, c is velocity of light, lambda is wavelength. So now we know terminology used in spectroscopic techniques, and when light interacts with matter, there could be two types of spectra. One is absorption spectra and another one is emission spectra. And when organic molecules absorb UV visible radiation, they undergo electronic transitions, which is known as absorption spectra. And when photon energies associated with infrared are not large enough to excite electrons, they can only vibrate bonds between atoms in the molecules. So this kind of spectra resulting is called infrared spectroscopy. Representation of light waves of different wavelength showing which region causes what transition. Here, ultraviolet region causes electronic transitions because of absorption of radiation, UV radiation, and infrared region, which is having higher wavelength radiations, cause vibrational transitions, which is called infrared spectroscopy. Now, coming to the actual infrared spectroscopic absorption or absorption spectroscopy, we have infrared spectroscopy represented in this cartoonistic picture with lower 5 bands and upper 5 bands, two types of bands. Lower 5 bands are called ground states or ground vibrational states. Upper 5 bands are called excited vibrational states. And the leftmost wave-like drawing is to represent infrared radiation falling on the sample, and blue balls here on the lowest energy state, which is lowest vibrational state, which is nu 0, are hit with infrared radiation. Because of that, absorption of energy will occur, and some blue balls will go to nu 1 state, which is a little higher than nu 0 state. When this kind of transition occurs, the energy resulting will be h nu 1 minus nu 0. And if this red ball, which is in the nu 1 state now, if it absorbs infrared radiation further, it will go excited to nu 2 state. In this case, it is having energy h nu 2 minus nu 1, which is called overtone. So like this, infrared radiation will cause energy transitions in the form of vibrational transitions. So basically, infrared radiation will have three components in it, or it can be divided into three types: near infrared, mid infrared, and far infrared. Near infrared lies near to the visible region. Far infrared is closer to the microwave region, and in between these two regions whatever infrared lies is called mid-infrared region. Near-infrared region, mid-infrared region and far-infrared region will become essential when we go towards advanced infrared radiation techniques. And everyday observation can hint us that when you heat a metal rod, it emits red colored radiation after it gets hot. So based on this analogy, we can get an insight that primary source of infrared radiation is thermal radiation, heat. So when you heat some sample, it agitates atoms and molecules present in the sample, and higher the temperature, more will be the atoms and molecules move, and more will be the infrared radiation they produce. Surprisingly, if you look into this fact, which is even ice cube emits infrared radiation, we can generalize that any object radiates in the infrared. So basically, infrared spectroscopy is a useful technique to identify functional groups in organic molecules, and it is the result of molecular vibrational transitions that occur when light interacts with matter, especially infrared light interacts with matter. And there is another surprising thing, that is molecules are always vibrating. They don't rest even at lowest temperatures possible. Molecules will always tend to vibrate. So that's why 0 point energy in infrared radiation or infrared spectra will have certain value instead of zero value. For a molecule to be IR active, the vibration should give rise to a net change in dipole moment. This is very important, as IR active molecules only will give IR spectra. IR inactive vibrations will not give rise to any IR spectra. We will discuss this with the help of carbon dioxide molecule. In carbon dioxide molecule, as represented in this slide, V1, if you observe, black ball represents carbon, two red balls represent oxygens. Carbon dioxide molecule is a straight, it can be represented as a straight line because it is a linear molecule. Now if you observe V1, you can see that both oxygen molecules are moving away from the carbon at the same pace. They started moving away from the carbon at the same time, and they move at same pace. But before that, we will try to understand what is dipole moment and what is net dipole moment. As the name itself indicates, dipole moment is two poles, moment arising from two poles. So here in the molecules, dipole moment corresponds to the charge separation. For example, if you consider CO2 molecule, carbon is slightly electropositive than oxygens, because oxygens are obviously more electronegative atoms. So the charge on carbon can be represented in the form of delta plus, and oxygens we can represent the charge on them as delta minus. Because of this charge separation, there is a net dipole moment. In the resting CO2 molecule also there is a net dipole moment. But if you consider V1 situation, two oxygen atoms that are bonded to carbon with the help of double bonds are moving away from carbon, and this kind of movement is called stretching, and specifically this kind of stretching in which both the oxygen atoms are moving away at the same pace from the central atom is called symmetric stretching. In the type of symmetric stretching vibrations, we don't see any net dipole moment change there is no change in the dipole moment. There is no change in the net dipole moment. And that's why these kinds of symmetric stretching vibrations in CO2 molecules will not be IR active, because there is no net dipole moment change. To get an idea about net dipole moment change much deeper, we will go directly to the V3 example in the same slide. Here V3 is asymmetric stretching, asymmetric CO stretch. The same CO2 molecule in which one oxygen atom is moving away from carbon, as represented by the left red ball, and another oxygen atom is moving towards carbon, which is represented by the red ball on the right side. So here in this representation, one oxygen is moving away from carbon and another oxygen is moving towards carbon. In this scenario, we can expect that there is a net dipole moment change. This kind of stretching vibration observed in CO2 molecule that corresponds to net dipole moment change is called asymmetric stretch, and it is very much active in IR. So this kind of stretching, which is asymmetric stretching vibration, will give IR spectra. But symmetric CO stretching in IR spectra will be inactive. In a similar way, we have bending modes also for CO2 molecule. If you look at V2 representation, we have two types of bending, which are one is in plane bending and another one is out of plane bending. In plane bending occurs when you put CO2 molecule on a paper, carbon moves up and two oxygen atoms move down. This is called in plane bending. But when carbon moves, when carbon and oxygens move in opposite directions out of plane of paper, those are called out of plane of paper bending vibrations. So there are four fundamental vibrations occurring in CO2 molecule. This is a typical IR spectrophotometer, wherein the right side is the instrument wherein you put the sample, and the left side is the interface where you collect the data. The data is represented in the form of IR bands. To understand it much further, we have a simplified infrared spectrophotometer cartoon here, in which infrared source, which is the leftmost red ball, which is infrared source, it falls on the sample that is sandwiched between two NaCl plates, and detection electronics and computer interface are connected to this. And this detector determines frequencies of infrared absorption and plots them on a chart. And in the chart, we have frequency as the x-axis and intensity of absorption as the y-axis. Absorption peaks are IR bands here. So this is a typical representation of IR spectra. We will see some examples, like for example in this case, we have a molecule that can be characterized by its molecular vibrations based on the absorption and intensity of specific infrared wavelengths. Here we have taken water example. Water is not it is not a linear molecule, but it is non-linear molecule, whereas CO2 is a linear molecule, water is non-linear. So it has OH bending and OH stretching vibrations that is represented in this slide. In a similar way, we have infrared spectroscopy of isopropyl alcohol here, and the absorption bands, IR absorption bands, can be represented in this way. On the y-axis, we have percentage transmittance, which will give us IR bands as values, and on the x-axis, we have wave numbers, which are represented in centimeter inverse units. So isopropyl alcohol, otherwise known as isopropanol, which we use in hand sanitizers and all. So isopropyl alcohol has OH stretching, CH stretching, CH and OH bending, CC stretching, CO stretching, CC and CO bending. So there are several characteristic functional group vibrations occurring in isopropyl alcohol, and based on these IR bands we can determine what is what.